Hello, welcome to my presentation. My name is Kyriakos-Chondrogiannis and I'm a PhD student at ETH Zurich. This work is a collaboration with Konstantina Koulatsou and Professor Charis Gantes. The institutions involved in this project are the National Technical University of Athens and ETH Zurich. This study is on the buckling verification of the manhole area of steel wind turbine towers with the use of nonlinear finite element analysis. In an outline, my presentation will include a small introduction, then the description of the investigated geometry, the numerical models that have been created, and the nonlinear finite element analysis that have been performed. A comparison of those results to analytical calculations is further offered. And towards the end, a comparison of the typical stiffened geometry to some unstiffened or partially stiffened solutions is studied. This presentation will conclude with the main observations of the study. As for the fabrication of a steel wind turbine tower, this includes first the cold curving of the steel sheets, then the welding of the parts both in the longitudinal and in the circumferential directions, as well as for the ring flanges which will connect the individual parts. Of course, towards the bottom of the tower, the manhole area is located, which will be the main focus of this study. And at the end, the fabrication of a tower includes, of course, the painting and the internal mechanisms of the tower that are required. As for the erection of the tower, first the preparation of a concrete foundation is required, then the transportation of the individual parts and lifting of those to the correct position is included before being bolted with bolt connections between the ring flanges of the individual parts. As for the specific geometry that is used in this study, it includes a 120-meter tall tower that has 5 cylindrical parts of a diameter 4.3 meters and an upper conical one of variable diameter, but this is not the main focus of this study. What is the focus of the study is the manhole area of the tower, which is located towards the bottom of the tower. And apart from the obvious opening, it includes a transverse door stiffener with thickness of 60 millimeters and thickening of the shell of the tower close to this area with a variable thickness of from 58 to 75 millimeters. As for the models, we have created finite element models and have simulated the ring flanges with beam elements, the shell of the tower with shell elements, as well as for the transverse door stiffener. As for the boundary conditions, we have considered full fixity at the base of the model and the free end at the top of it. As a first step, we have studied the results from the linearized buckling analysis. We have performed parametric analysis to evaluate the effect of the direction of the actions on the critical loads. We can see at the graph at the top the directions that we have considered and end up to the conclusion that the critical direction is that of the 45 degrees for the shear force and respectively to the moment that this produces. As for the 3 first buckling modes of the structure, we can observe that they are similar both in terms of the shape as well as for the critical load. In order to perform geometrically nonlinear analysis, we need to determine the initial imperfections of the geometry of the structure. We have followed the provisions provided in the Eurocode, where 3 fabrication classes are explained, and depending on the fabrication class, there's a different level of deviation of the structure from the idealized geometry. So we have performed geometrical and material nonlinear finite element analysis with the inclusion of imperfections. Once again, we have performed parametric analysis for varying direction of the loading, as well as for parametric analysis in terms of the shape of these initial imperfections. These are defined as the shape of, following the shape of an individual buckling mode, or a superposition of more than one. Once again, we can observe good agreement between these results and the ones from the buckling analysis, which conclude that the 45-degree angle direction is the worst case scenario. We can observe the equilibrium paths of the system, and for different fabrication classes, the higher the fabrication class, the more the strength and the capacity of the structure. We can also see the deformed shape of the system, as well as the stress that is the resulting stresses. And we can see that they follow similar patterns between the different fabrication classes. We have also performed analytical calculations following the ones that are offered in the Eurocode, which include the study in the axial direction, the circumferential one, and as well as to the shear buckling. And additionally, the combination of buckling for all directions concludes to the ultimate capacity of the structure from these analytical derivations. For this purpose, we need to define a critical length, and we focus on the bottom part of the tower. The critical length is defined between two ring flanges, and we need to categorize the part depending on the length, diameter, and thickness of it, which is considered classified as a long cylinder. As for the boundary conditions, we consider the bottom of the tower to be clamped, fully fixed, and all at the levels of the ring flanges, the boundary conditions are considered to be restricted by those flanges, representing pinned connections. So comparing these results of the analytical derivations to the numerical models, focusing on the peak fabrication class, from the numerical analysis, we can spot the most unfavorable result and compare it to the analytical output after applying the partial safety factor, and we can observe that there's good agreement between the two solutions. Finally, there is investigated for some partially unstiffened or completely unstiffened solutions. So we compared 4 models. The first one is the original one. The second is a partially stiffened, which has the transverse frame around the manhole area, but does not have the thickening of the door plate. The other one has the thickening of the door plate, but not the transverse stiffener. And the fourth one does not have any kind of stiffening. As for the linearized buckling results, we can observe that models that have the transverse stiffener have significantly increased critical load. However, in terms of the ultimate capacity of the geometrically and material nonlinear finite element analysis with the inclusion of imperfections in a similar way that we did before, we result to similar capacities, which is somehow explained due to the fact that the system is highly influenced by material nonlinearity. since the ultimate capacity is way lower than the one predicted from the backlink analysis. And we can also see we can also observe that for the cases that the transverse stiffener is not present, that the failure is located at the door, at the opening, close to the opening, whereas for the cases that the stiffener is present, the failure is directed towards the upper part of the model. In conclusion, we have performed numerical investigation of a 120-meter tall wind turbine tower, applying realistic wind loads, and we investigate the backlink response near the manhole opening. The effect of the load direction with respect to the manhole area is evaluated, and we have also come to the conclusion that the effect of the initial imperfection play a significant and considerable role in the ultimate capacity of the design. We can also observe that stability of the manhole area is influenced significantly by the presence of the transverse stiffener, where the failure is directed away from this area. However, we observe that the ultimate capacity remains somehow close to the original one. And we also can observe that the thickening of the door plate is less effective towards this direction. This concludes my presentation. Thank you very much. And this project has received funding from the European Union's Horizon 2020 Research and Innovation Program.